And the first speaker of today will be Mara Lazaros from our institute here, and she will talk to you about metals and metalloids in terrestrial environment.
You heard I work at the analytical toxicology unit, focusing mostly on ecotoxicology, terrestrial ecotoxicology. And probably these days you already had a feeling that toxicology is a mix of different scientific branches. The same goes to ecotoxicology. It's a mix of ecology, physiology, veterinary toxicology, and so on. So ecotoxicology looks at the impact of contaminants on individuals, but also wider on populations, natural communities, and ecosystem. At our institute, we have scientists that look at organic contaminants. You heard about that last days. And at my unit, we are focusing more on inorganic contaminants. So specifically on metals and metalloids. But let's go to the basics for the introduction. You know that there are metals, non-metals, but also some elements that combine the characteristics of both groups. These are, for instance, arsenic and selenium. Also, you probably met the term heavy metals. It's a more colloquial term, which groups metals with high density, but it's a term that it's not that much toxicologically informative, because in this group of metals you have essential metals, you have potentially toxic and toxic elements. So don't try to don't use this term, but be familiar what it stands for. So elements are well characterized, but why do we keep studying them? Because they are persistent. They can be transported long distance by air, and they can accumulate in organisms and cause systemic toxicity there. And probably you've heard about Paracelsus these days, about his famous saying that all compounds can be poison, but only the degree of toxicity is determined by the dose. That is why some elements at the periodic table are marked with green, they're essential. Some of them can also be toxic, so you see the orange color, and by red color I colored the metals that don't have biological role in the organism. So metals and metalloids originate from natural, but also from anthropogenic sources. They circle among biotic and abiotic compartments, and they can be transferred between different trophic levels. For major biotic compartments, so some plant or animal species, and for most prominent metals and metalloids, science determined the thresholds of toxicity. So these are dose or concentration that will most probably cause some toxic effect in the specific compartment. These concentrations are then included or in the legislation or are published in some papers as reference ranges that we use in interpretation of our ecotoxicological studies to interpret our measured concentrations. You will see in next examples. This is first example of our project from northeastern Croatia, where we examined the impact of natural gas treatment plant on surrounding ecosystem using the biotic indicators relevant for terrestrial food chain and also for human health. Natural gas contains contaminants as, for instance, mercury, arsenic, natural occurring radioactive material. So purification efficiency in the treatment plant is of relevance for the surrounding environment where this natural gas will be used. So we sampled the soil on different locations around the treatment plant, mosses, earthworms, samples from cows from nearby village Molve, and tissues from wildlife, from pheasants and hares, because this area is predominantly agricultural area. Our results showed that exposure to metals and metalloids for all biotic compartments is negligible, but we found that arsenic and zinc in soil was higher than it was legally prescribed for agricultural soil. We also advise public to freely and safely consume all cattle and game products, but they should avoid eating liver and kidneys from these hares and pheasants because of high cadmium and lead. A second example is related to West Croatia. So the area naturally rich in cinnabar ore. It is mercury sulfate. And very near in neighboring Slovenia on the north is a former mercury mine in Idria, which is famous as being the second world largest mercury mine after Almaden in Spain. Maybe some of you come from Spain and are familiar with Almaden. In Idria, this mine has worked for over 500 years. Now it's closed. And mercury was used for long in gold and silver mines in the New World for extraction of these precious metals using the process of amalgamation. Our interest was to examine if this naturally rich soil rich with mercury, can transfer mercury to mushrooms, which are known accumulators of toxic metals, in the concentrations that can be toxic to humans that consume those mushrooms. We have chosen to sample the most consumed wild mushrooms from Boletus genus. It's porcini, ceps. And for comparison, we sampled mushrooms from different locations in Croatia. So the results you can see in black columns, results of mercury in mushrooms, and we found that 13% of these mushrooms had cadmium concentrations higher than its than the legal limit in the legislation. Also, we saw that with higher altitudes, you can find higher lead and radionuclide cesium because of the higher amount of rain and snow that falls there. Again, we advised public to limit consumption of these mushrooms to maximum once a week because of the high cadmium and lead that we found there. As I said before, metals and metalloids can be taken up by inhalation, ingestion, and or dermally in each trophic level, and can be accumulated in the organism by a process that we call bioaccumulation. For some metals and metalloids like mercury, concentrations rise with higher trophic level. So we wondered if animals in Croatian habitat that are on the top of food pyramid are really exposed to higher levels of metals and if health hazard exists. In our studies, we covered different types of animal species, and also we took some food items that are produced in a forest ecosystem. One of our recent studies on griffon vultures from island Tres focused on their exposure to lead. Vultures are obligate scavengers that are on the top of food pyramid, and they prey on mammalian carcasses. Lead ammunition left in the game carcasses after hunting was detected as important source of vulture intoxication, leading to population decline worldwide. Also, the most prominent are in Portugal, Spain, and in the North Africa. So we studied vultures that were received in the rehabilitation center for vultures in Bali on island Ceres, and they were mostly juveniles. And we saw that 36% of those animals had lead in their blood above what is considered background concentration. 8 animals of those 25 had lead blood in characteristic for subclinical lead poisoning, and one bird had even higher concentrations of lead that were corresponded to a clinical lead poisoning. And in this bird, we also saw the pathology in feather growth that can be connected to lead-related adverse effects. Also, we studied metals in different Croatian hunted wildlife, again, because of the relevance for terrestrial food chain and for human health, because humans consume those wild animals. We found that brown bear was a species that contained the highest concentrations of toxic metals, and concluded that kidney was a target organ for cadmium and mercury bioaccumulation. And these conclusions gave us indication to further explore the exposure to toxic metals among 3 apex large carnivorous in Croatia, which share their habitat with golden jackal. So he was also included in the study. So they were all apex predators. And again, brown bear was shown as a species to accumulate the highest levels of toxic metals, especially cadmium and lead in the kidney cortex. Apex predators consume food items that already accumulate toxic metals from the surrounding environment. So their exposure originates from the food, but also from soil, water, and air. So except the internal dose of metal, and by that I mean the concentration that is in some organ, there are also important drivers of toxic effect that should be taken into account when we do some ecotoxicological studies. And these are sex, age of animal, genetics, physiological state. So if they are gestating, if they are lactating, also the season, life history, and so on. So as in epidemiological studies with humans, also in these ecotoxicological studies, they should be taken into account as very important. As our fundamental challenge was to assess the health risk for this specific species, except internal dose of metal, we measured also the effect that metal caused. We know that oxidative stress is a most prominent mechanism that of toxic metals. And that's why we used biomarkers of oxidative stress to look if metal causes some adverse effect. When choosing the tissue for sampling, we should have in mind where the specific contaminant is being accumulated in the organism regarding its biochemistry. And if we are interested in recent exposure of an animal, and then we will use blood for monitoring, or if we are interested in the longer period of exposure, and then we will use, for instance, bone for lead monitoring, or soft tissues like liver or kidney for monitoring cadmium and mercury. Here you can see the distribution of lead in bare tissues on a logarithmic scale. And again, the highest accumulation was noted in the bone, then in the kidney, liver, and so on. And after we looked at the distribution, we focused on the kidney and liver as target organs of many metals. And we found that in Croatian population of brown bear, about 5% of bears had hepatic lead above toxicity benchmark. Also, in the kidney, we found in 1% of population or less that cadmium and lead concentrations were also above these toxicity benchmarks. Further, we explored if age and sex were influenced the distribution of toxic metals in the tissues of brown bear, and we saw that in that lead accumulated with age in bone, and for liver and kidney, we saw that cadmium and lead increased with higher in older animals. Also, females had higher concentrations of cadmium and mercury than males. So we concluded that our but brown bear, older females are sensitive group in this Croatian population. And severity of health risk is even greater if we have in mind that adult females give birth and nurse their cubs. And so the high concentrations of toxic metals in their organism will be transferred to their young. That is why we looked at mother cub pairs. And as you can see, cubs had significantly lower cadmium and mercury in kidneys than their respective mothers. However, trouble was the high transfer of lead from mothers to cubs, resulting in similar or even higher concentrations in the kidney of cubs. We know that young animal that is still developing is much more sensitive to effects of toxic metals. So the health hazard is even greater in this population group. I mentioned already that the most informative parameter in ecotoxicological studies are markers of effect. In blood of bears, we measured protein metallothionein, which has a high affinity for binding toxic metals. We measured activity of antioxidative enzymes and one parameter of lipid peroxidation. And we found that as in bears that had higher concentration of lead in their blood, activity of antioxidative enzyme, superoxide dismutase, increased. Another study of effect in brown bears focused on the influence of toxic metals on reproductive hormones and cortisol. And we saw the highest influence on the hormone testosterone. Again, statistical analysis showed the importance of including biological variables like sex, age of animal, but also the sampling variables were shown as very important. So how the animal was sampled. So our conclusions based on results gained so far for brown bear pointed that in the general population, we do not expect adverse health effects because of the toxic metals, but in some sensitive groups in the population, we can expect some health risk because of the high lead levels.